There is something almost unreasonable about the way we look up. We always have, long before there were names for what we saw. Before there was language precise enough to tell a star from a wandering light, human beings were already tilting their heads back at the night and feeling that quiet pull, the wordless sense that the sky was asking us something. If you have lived long enough, you have felt it more than once. It does not fade with age. It sharpens. What follows is not a textbook, and it is not a list of facts you could read off a chart. It is closer to a portrait, 8 worlds, each with its own character, its own hidden life, its own way of overturning an assumption you did not even know you were carrying. And all 8 were born together from the same event about 4.5 billion years ago. That birth obeyed a law you already understand without knowing its name. A vast, slow cloud of gas and dust collapsed under its own gravity, and as it shrank, it spun faster and flattened into a disk. The very same principle that makes a spinning skater speed up when she draws her arms inward. Physicists call it the conservation of angular momentum, and it is written into the oldest rocks we possess. Meteorites, the most ancient solid material we can hold in our hands, date this moment to 567 billion years ago. Within that spinning disk, grains collided and stuck, growing from dust to pebbles, from boulders to worlds. The sun claimed more than 99% of all the material for itself. Everything else, every planet, every moon, every one of us, was assembled from the leftover fraction of 1%. We are, quite literally, the crumbs from the edge of the table. But here is the detail worth sitting with. Same origin, same cloud, same law. And yet these 8 worlds turned out almost nothing alike. To understand how, we have to begin where almost no one expects the strangeness to start, with the smallest planet, the one we nearly ignored. Mercury should be simple. It is the closest planet to the sun, and by every reasonable expectation, it ought to be a dead, scorched rock, baked into silence by its nearness to the fire. On its sunlit side, temperatures climb to around 430 degrees Celsius, hot enough to melt lead. That much matches the expectation. And then we looked closer. Inside craters near its poles that sunlight has never once touched, across billions of years, there is ice, real water ice, confirmed by NASA's Messenger spacecraft, which orbited the planet from 2011 to 2015. Sit with that contradiction honestly. A world hot enough to melt metal in the daylight, cradling frost in the permanent dark of its own craters, separated only by the angle of a wall of rock, fire and ice on the same small world. But the deeper puzzle is the one you cannot see. Mercury has an iron core that fills roughly 85% of its radius, proportionally the largest metallic heart of any planet we know. A world this small has no business carrying a core this large. The leading explanation is violent. Early in its history, Mercury may have suffered a colossal collision that stripped away much of its rocky outer layers and left the dense metal interior exposed. What we see today may be the surviving core of a planet that was once far bigger. And that iron heart is not dead. Mercury still generates a genuine magnetic field, weak, only about 1% of Earth's, but real and coherent. A magnetic field requires a moving, molten interior, and a planet this small should have cooled and frozen solid long ago. That it has not forces scientists to rewrite the thresholds they thought they understood. The minimum size, the minimum heat, the minimum everything required to keep a world alive inside. Mercury hides its strangeness beneath a scorched surface. You have to go deep to find it. The next planet is the opposite. It wears its contradiction on the outside, and from a distance, it looks almost exactly like home. On paper, Venus should be Earth's closest sibling. Same size, same rocky composition, formed in the same neighborhood of the same disk. For decades, scientists genuinely believed it might hold oceans beneath its thick clouds, even life. The expectation was so strong that they called it Earth's twin before they knew better. Then we looked closer, and almost everything was wrong. Venus spins backward, not in some technical sense that needs a footnote, backward. If you could stand on its surface and survive, you would watch the sun rise in the west and set in the east. Nearly every planet turns in the same direction, the inheritance of that first spinning disk. Venus rotates the opposite way, and so slowly that a single day there, 243 Earth days, lasts longer than its entire year of 225. The planet finishes its trip around the sun before it finishes turning around once. The surface beneath that strangeness is a vision of something ancient and merciless. The temperature holds at about 465 degrees Celsius. Day and night, poles and equator alike, hotter even than Mercury, though Venus sits nearly twice as far from the sun. The atmospheric pressure at ground level is roughly 92 times that of Earth, the crushing weight you would feel a kilometer beneath our oceans. Every Soviet probe sent there in the 1970s and 80s was crushed or cooked within hours. The longest lasted just over 2 hours before going silent. How does the more distant twin become the hotter one? The answer is a phrase that deserves our attention: a runaway greenhouse effect. Venus is wrapped in dense carbon dioxide, with clouds of sulfuric acid drifting through it. Sunlight enters, warms the ground, and the heat that tries to escape is trapped. Over time, the trapping fed on itself, driving temperatures higher until any oceans that may once have existed boiled away entirely. What remains is a sealed furnace that can never cool. Venus is the twin that went the other way, proof that a world can begin with every advantage and still end in ruin, which forces the real question of this entire journey. If Venus had everything and still failed, what exactly went right on the one planet where the balance held? We tend to think of Earth as the ordinary planet, the baseline, the normal one, the world against which all the others look strange. Turn that around. From the perspective of the rest of the solar system, Earth is the outlier. It is the only known place where water exists as solid, liquid, and vapor all at once. The only world with drifting continents, breathable oxygen, and a surface that holds, almost impossibly, in the narrow band where liquid water can pool and stay. Scientists call that band the habitable zone, sometimes the Goldilocks zone. Not too hot, not too cold, but the region around a star where liquid water can survive on a planet's surface. Earth sits comfortably inside it, but a good address is not enough. Mars sits near the same zone and froze. Venus sits near the other edge and burned. Earth threaded the needle, and it needed far more than luck of position to do it. Consider the quiet machinery that keeps this world in balance. A molten iron core generates a powerful magnetic field, an invisible shield that deflects the sun's charged particles and keeps our atmosphere from being stripped away, the very protection Mars appears to have lost. A single, unusually large moon steadies the tilt of our axis and holds our seasons even across the ages. Plate tectonics slowly recycles the crust and regulates carbon over millions of years, acting like a planetary thermostat. Remove any one of these, and the story might have ended the way Venus did. None of it was guaranteed. Each of these features could have been absent, and in most of the worlds we have now surveyed, they are. What we experience as the plainness of ordinary life, rain, seasons, breathable air, water that simply flows, is the product of a convergence so specific that we are still cataloging the ways it could have failed. Earth is not the normal planet. Earth is the rare one. But if the conditions for life are this delicate, a haunting possibility follows. Because right next door, on a rust-colored neighbor, there are the dried beds of ancient rivers. And rivers once meant water, which means the question of whether Earth was ever truly alone has never gone quiet. Mars today is a cold, dry, rust-colored desert. Its thin atmosphere is less than 1% the density of ours, its surface swept by dust and locked in a deep freeze. To stand there would be to stand in a place that looks as though it was always dead, and yet the ground itself tells a different story, one written in the shape of the land. Orbiting spacecraft have photographed features no dry world should possess: branching valley networks that look unmistakably like riverbeds, sprawling deltas where sediment once fanned out as it does at a river's mouth on Earth, and vast basins that resemble the floors of ancient lakes. NASA's rovers have gone further, rolling across these terrains and finding, locked in the rock, minerals such as clays and sulfates that form only in the presence of liquid water. The evidence is not subtle. Water once flowed on Mars, perhaps in great quantity, perhaps for a very long time. So, what happened? The explanation returns us to a theme we have already met. Mars is smaller than Earth, and its interior cooled faster. As its core solidified, the planet appears to have lost the churning dynamo that once powered a protective magnetic field. Without that shield, the solar wind, the constant stream of particles from the sun, slowly eroded the Martian air across hundreds of millions of years. As the atmosphere thinned and the pressure dropped, the water that could no longer stay liquid froze into the ground or escaped into space. A living-looking world became a fossil. This is why Mars holds so much of our attention and so much of our machinery. The question is no longer whether water existed. That much is settled. The question is whether, in those warmer and wetter ages billions of years ago, anything ever stirred in that water. We have not found it, but we have not stopped looking. And every sample the rovers drill is another attempt to read a page of a book that may contain a single sentence about life, or none at all. Mars shows us how a world can lose everything, but loss is only one kind of drama. Cross the asteroid belt, and the scale of everything changes into a world so vast and so violent that it has been staging the same storm since before the telescope was invented. Jupiter belongs to a completely different order of thing. It is so large that more than 1/300 Earths would be needed to fill its volume, and it holds more mass than all the other planets combined, twice over. It has no solid surface to stand on. It is a churning ball of hydrogen and helium, a would-be star that never grew massive enough to ignite, and across its face runs the most famous storm in the solar system. The Great Red Spot is a hurricane so enormous that the entire Earth could vanish inside it. What makes it extraordinary is not only its size, but its endurance. Astronomers have watched this storm through telescopes for at least 3.5 centuries. It was raging before the founding of modern nations, before the invention of the light bulb, before anyone alive today drew a single breath. A storm on Earth lasts days. This one has outlived the entire history of the instrument that revealed it. How can a storm persist that long? On Earth, hurricanes weaken and die when they cross land, torn apart by friction with the ground. Jupiter has no ground. There is nothing solid to slow the winds, no coastline to break them, only an almost bottomless atmosphere in which the storm can spin on and on, fed by the planet's own internal heat. Jupiter radiates more energy than it receives from the sun, an inner furnace that keeps its atmosphere in ceaseless, turbulent motion. Winds inside the Great Red Spot have been clocked above 400 kilometers per hour. And yet even this ancient giant is not truly permanent. Careful measurements across the past century show the Great Red Spot is slowly shrinking, growing rounder and smaller than it appeared to observers in the 1800s. We may be living through the long, quiet closing chapter of a storm, older than any storm we could name. Nothing here, it seems, not even the most enduring feature we know, stands entirely outside the reach of change. But Jupiter is far more than a spectacle to admire from a distance. Its sheer size gives it a role most people have never considered. A quiet, powerful role that may have shaped the entire course of life on our own planet. There is a way of looking at Jupiter that turns it from a distant curiosity into something deeply personal. That immense gravity, the pull of a planet more than 300 times the mass of Earth, does not only govern its own moons and storms, it reaches across the solar system, tugging at the paths of comets and asteroids that stray inward from the frozen outer dark. For much of the 20th century, astronomers came to think of Jupiter as a kind of gravitational bodyguard. The idea was simple and compelling. As icy bodies fall inward toward the inner planets, Jupiter's enormous gravity intercepts many of them, either flinging them back into space or drawing them in to strike the giant instead of striking us. We do not have to imagine this. In 1994, the world watched as comet Shoemaker-Levy 9 was torn apart by Jupiter's gravity and slammed into the planet in a string of impacts, each scar in the clouds larger than the Earth. The full picture, it turns out, is more nuanced than a simple story of a protector. More recent studies suggest Jupiter's role is genuinely double-edged. Its gravity deflects many dangerous objects, but it can also, on occasion, nudge others onto paths that carry them toward the inner solar system. The giant both shields and disturbs. Science rarely hands us a hero as clean as we would like, and Jupiter is no exception. It is less a guardian at the gate than a vast force whose influence cuts in more than one direction. Still, the larger truth remains striking. The presence of a massive planet in the outer system has profoundly shaped the environment of the inner worlds over billions of years. The frequency of impacts, the delivery of water and raw material, the long stretches of calm that complex life seems to require. Our fate has never been ours alone. It has been entangled all along, with the movements of a giant we can see with the naked eye, but rarely think to thank or to fear. If Jupiter commands the solar system through its mass, the next world commands our imagination through its beauty. But that beauty, we now know, is not built to last, and its ending has already begun. No image of the solar system is more instantly recognizable than Saturn wearing its rings. They are so much a part of how we picture the heavens that it is easy to assume they have always been there and always will be. Both assumptions are almost certainly wrong, and the truth is stranger and more moving than the postcard suggests. The rings are not solid bands. They are countless separate pieces of ice and rock, some as fine as dust, some as large as a house, each one an independent moonlet tracing its own orbit around the planet. They are astonishingly wide, spanning a distance that would nearly reach from the Earth to the Moon, and yet astonishingly thin, in most places only about 10 meters from top to bottom. Scaled down to the width of a football field, they would be far thinner than a sheet of paper. Here's the part that changes how you see them. Data from NASA's Cassini spacecraft, which studied Saturn up close until 2017, revealed that the rings are slowly raining down onto the planet. Icy particles, nudged by Saturn's magnetic field and gravity, drift inward and fall into the atmosphere in what researchers have called ring rain. At the measured rate, the rings are not a permanent fixture at all. Current estimates suggest they could largely disappear within roughly 100 million years. On the scale of a planet's life, that is the blink of an eye. There is something quietly profound in that. It means the rings may be young, perhaps only a few 100 million years old, which would mean the dinosaurs walked an Earth whose night sky held a ringless Saturn, and it means we are living inside a rare and fleeting window in which this crown exists to be seen at all. Of all the beings who might ever look up across the vast history of this solar system, we happen to be among the few who arrived in time to witness the rings before they fade. Saturn is a lesson in impermanence, hidden inside a thing of beauty. The next world offers a different strangeness altogether. A planet that does not spin the way any planet should, as though something long ago struck it and knocked it clean off its feet. Every planet spins, and nearly all of them spin in much the same way, turning upright, more or less, like tops rotating on a table, their axes tilted at modest angles. Earth leans about 23 degrees, which is why we have seasons. Then there is Uranus, which does not spin upright at all. It lies on its side. The axis of Uranus is tilted about 98 degrees, so far over that the planet essentially rolls around the sun rather than spinning beside it. Picture a top that, instead of standing and turning, has fallen onto its side and is rolling across the floor. That is Uranus, circling the sun on its side through an orbit that takes 84 Earth years to complete. The result is a world of almost unimaginable seasons. Each pole spends roughly 42 years bathed in continuous sunlight, then 42 years plunged into unbroken dark. What could tip a planet so completely off its axis? The leading explanation is violence on a scale we can barely picture. Early in the solar system's history, when large bodies still roamed and collisions were common, Uranus may have been struck by an object several times the mass of the Earth, a blow so tremendous it knocked the entire planet over and left it spinning on its side ever after. And there is a second riddle bolted onto the first. Such a collision should have heated the interior, yet Uranus radiates almost no internal heat at all, while Neptune, nearly its twin, pours out almost 3 times the energy it receives. Scientists suspect a deep layer of exotic material may be trapping the heat inside, but what that layer actually is, no one is certain. Uranus is often overlooked, a pale blue-green world so distant it was the first planet ever discovered with a telescope rather than the naked eye, found only in 1781. But its quiet strangeness carries a lesson that runs through this whole journey. The solar system we see is not the product of gentle, orderly assembly. It is the survivor of an age of collisions, of worlds struck and stripped and toppled, of a chaos that has only since faded into the appearance of calm. And if Uranus was found by telescope, the next planet was found by something more remarkable still, not by looking at all, but by pure mathematics. It was discovered on paper, in the pages of a calculation, before any human eye confirmed that it was truly there. Neptune is the last of the major planets, a deep blue world so distant that its sunlight takes more than 4 hours to arrive, against the 8 minutes it takes to reach us. At that distance, in that cold, You would expect a still and sluggish place, a planet too far from the sun's warmth for much drama. Neptune shatters that expectation completely. This frigid, faraway world has the fastest winds ever measured on any planet in the solar system. Gusts in its atmosphere have been clocked above 2,000 kilometers per hour, faster than the speed of sound on Earth, faster than any storm our own planet could produce. It is one of the great unsolved puzzles of planetary science, how a world so starved of solar energy can drive winds of such staggering violence. Something deep within Neptune, some internal source of heat and motion we do not yet fully understand, powers a fury the distant sun could never explain. But the most remarkable thing about Neptune is how it was found. In the 1840s, astronomers noticed that Uranus was not moving quite as the laws of gravity predicted. It was being subtly pulled off course by something unseen. Rather than sweeping the sky blindly, mathematicians used Newton's law of universal gravitation to calculate where an unknown planet would have to be to cause exactly that disturbance. In 1846, astronomers pointed a telescope at the predicted spot, and Neptune was there, within a degree of where the equations said it must be. Pause on the size of that achievement. A planet discovered not by observation but by reason, conjured from a page of arithmetic and then confirmed in the sky. It stands as one of the most triumphant demonstrations in the history of science that the universe obeys laws precise enough for the human mind to predict what it has never seen. Neptune is proof, written across more than 4 billion kilometers of space, that our grasp of gravity is not a guess, but a working key. With Neptune, we reach the edge of the classical solar system. But the edge is not the end. Beyond it lies a frozen frontier we have only begun to explore. And it may hold the very thing we have been chasing since we first asked whether Earth was ever truly alone. For most of human history, the story of the solar system ended at Neptune. Beyond it, we imagined, lay only empty dark. We were mistaken. Stretching outward past the last great planet is a vast, cold region of dwarf planets, icy bodies, and distant moons, a realm we are only now beginning to chart, and one that has quietly become the most promising place to search for life beyond Earth. Pluto, once counted as the 9th planet and reclassified as a dwarf planet in 2006, turned out to be far more than the frozen wasteland many expected. When NASA's New Horizons spacecraft flew past in 2015, it revealed towering mountains of water ice, vast smooth plains of frozen nitrogen, and signs of activity on a world scientists had assumed was long dead. Even out there, in the deep cold at the fringe of the sun's reach, a small world was still doing something. The lesson of this whole journey held once more. The outer solar system is not the still, lifeless place we imagined. The most tantalizing discoveries, though, are the hidden oceans. Beneath the frozen crusts of certain moons, Europa, which orbits Jupiter, and Enceladus, which orbits Saturn, there is strong evidence of vast liquid water oceans, kept warm not by the distant sun, but by the flexing tidal pull of the giant planets they circle. Enceladus goes further still. It vents plumes of water vapor into space through cracks in its icy shell, and when Cassini flew through those plumes, it detected chemical ingredients associated with life as we know it. Liquid water, a source of energy, and the right chemistry, the three things life is thought to require, appear to sit together, right now, beneath the ice of a moon nearly 1.5 billion kilometers away. And past even the known worlds, the outer dark still whispers. For years, astronomers have noticed a handful of distant objects moving in a way that random chance struggles to explain, their orbits tilted and clustered as though nudged by something massive and unseen. Some researchers have proposed a hidden Planet 9 to account for it. It remains unconfirmed, a possibility still debated rather than a discovery, and honest scientists disagree about whether it is real. But it is a measure of how little of our own solar system we have truly mapped, that a world potentially larger than Earth could still be hiding at its edge. Which leaves us with one final reckoning. We have crossed the entire solar system, from the scorched rock beside the sun to the buried oceans at its rim. And when we step back to see all of it at once, a single sobering truth comes into focus. We began with a spinning cloud of dust and a law of physics, and we have traveled outward through fire, ice, storm, and frozen ocean. Now, at the end, look back at the whole of it. 8 planets, dozens of moons, rings that are already fading, worlds toppled by ancient collisions, a giant that both shields and disturbs, and in the middle of it all, one small blue world where the balance somehow held. Seen together, the solar system stops looking like a collection of separate wonders and starts looking like a single, intricate machine. And here's the truth our exploration of distant stars has made impossible to ignore. This machine is rare. In the decades since we began finding planets around other suns, more than 5,000 of them now confirmed, we have discovered systems utterly unlike our own. Giant planets orbiting closer to their stars than Mercury orbits ours. Worlds crushed together in tight, chaotic arrangements. Systems that would tear an Earth-like planet apart or fling it into the dark. The calm, spacious, layered order of our own solar system, with its small, rocky worlds tucked safely inside and its giant standing guard far out, appears to be far less common than we once assumed. That fragility is not a reason for fear. It is a reason for attention. Every mystery we have touched, Mercury's stolen mantle, Venus's runaway sky, Mars's ghost rivers, Saturn's dissolving crown, the buried oceans of distant moons, is a piece of the same larger lesson. The conditions that allowed us to exist, to look up, and to understand what we are seeing were neither guaranteed nor permanent. We are the crumbs from the edge of the table that somehow learn to comprehend the whole feast. That is not a small thing. It may be the most extraordinary fact in this entire story. So if this journey through the majestic and mysterious worlds of our solar system stirred something in you, a sense of wonder, a question you had never thought to ask, a renewed awe at the same sky that hangs over your own home, then I would ask something of you in return. Take a moment to subscribe to this channel so that we can keep exploring these mysteries together. Give this video a like so that others who share this curiosity can find their way here as well. And most of all, leave a comment below and tell me, of all the worlds we traveled to tonight, which mystery lingers with you the most? I read every one, and your questions often become the beginning of the next journey. Because the truth is, we have only just begun to understand the fragile, magnificent machine we call home. The sky never got smaller. We only stopped looking. And there is so much of it left to explore, together.